Hello and welcome back to another video with It's Dr. Dan, and what we are going to be looking at today is the anatomy of the atom, specifically looking at modern nuclear atomic theory. So we're going to be dissecting what the atom looks like and how did we get there. In this video, we're first going to start with looking at Dalton's atomic theory, which is what we start our journey on when we are learning chemistry, of how the atom is observed and how it has come up in our history. And the thing is that the atom, the whole idea with this has actually come up since the BC era, since the Greek times, where the word atomos was originally philosophized, that we were made up of tiny, very, very tiny particles. So this is not a new concept. It's been around for a very long time. It's been in development through observations and measurements and theories across many, many generations of scientists. Now, with Dalton, his whole idea was that every single element is composed of tiny, indestructible particles called atoms. Now, all these individual atoms, they can come in many different ways because they all have unique properties. So, for example, if I have a bunch of atoms of carbon all bound together under very, very high pressure, they can make diamonds. If I have chlorine atoms bound together, they make gases. If I have silver atoms all bound together, they will make metal bars, and they all are very, very unique and have their own individual properties because they are made up of that individual particle. Now, along with that theory, all atoms of that element, they all have their own unique mass, and they all have very unique properties which help them be distinguished from other elements. So for example, if I look at sodium, right, this is something we've talked about before. It is an alkali metal. It is extremely reactive. We've seen videos of it getting thrown in water and exploding. And even though it is a silver metal, if I kind of compare that to, let's say, silver, which is also a silver metal after its namesake, they might both be silver looking, but they're not the same element, right? One's sodium, one's silver, Ag versus Na. So the atoms, they have completely different properties. Sodium, it reacts violently with water, it'll explode. Silver, if you throw it in water, well, it's not going to do anything. It doesn't react, right? So they have their own unique properties. So now, other than them also having their own unique properties, one of the important thing about them is the atoms can combine together. They can chemically bond. So in the future, in other videos, you can see that, oh, they can go through covalent bonding, ionic bonding, and really be able to see how do they combine. Now, the thing is, they combine in specific ratios, meaning that we have a law of definite proportions. It is also known as the law of multiple proportions, meaning, for example, that we will always have whole number ratios of atoms bound together. So think of water. H2O, where the heck, why have you heard that your entire life? Where does that come from? And that is because if you think of the molecule, it has 2 hydrogen atoms bound to every 1 oxygen. It's in a ratio of 2 to 1. It would not be water if it did not have that ratio. Same thing right now as you breathe out and you feel your breath, right? What is that? Well, that's carbon dioxide, CO2. For every 1 carbon, there's 2 oxygens. It's once again a whole ratio. Now, that's not the only thing that comes out of that law. You can also see, being that H2O is 2 hydrogens and 1 oxygen, you can look up the masses of each one of those elements from the periodic table, and you could also add them up in order to get their complete atomic mass, which is very, very important for molecules. It's something that's going to be done a lot in your chemistry course. So adding up those masses is an important skill to really be able to see. Now, the issue with this, it does not explain everything about it. One thing that came up is that atoms were originally believed to be completely indivisible, meaning that they couldn't be split apart. But that was found out to not be completely true. How could you differentiate amongst these atoms other than properties? It's not enough. So there has to be additional theories. This is where they found out there was subatomic particles. So every atom is built up of protons, neutrons, and electrons to help understand what these atoms look like. When you learned how to read your periodic table, how to actually see how all these are represented, you learn about these particles. They still have the same letters. They do not have a charge. Electrons, so if you had a positive, a neutral, what's left is your negatively charged particle, electrons. So you have 3 different charges that are available to you. So every single element is made up of atoms, and every atom has protons, neutrons, and electrons that set them apart. Now, before we can really look into this, we have to, how do we put them all together? Are they all jammed in the same location in this atom? How are they all arranged? Well, it all came down to essentially physicists really for a good part of a century trying to really get an idea of, well, how do charges behave? And the easiest way to think about it is think of magnets. So as a kid, at some point in your life, you probably played with magnets and you tried to push them together, and no matter what, they would always slightly repel each other until eventually the opposite poles would be touching each other and be connected. This is where the idea of like charges repel each other, meaning that if you try to push 2 positive parts together, no matter what, you just can't seem to touch them. Same with 2 negative charges. The reason is they require a lot of energy for them to touch each other. They don't want to, right? They don't want to be near each other no matter what you do. Now, another thing that comes up is opposites attract, right? So that's something we hear our entire lives around romance, and it's even true down to the physical setting into your chemistry. It's inside of your atomic DNA, I guess, as well. And that's a positive and a negative are attracted to each other. When they are attracted, they release energy, so it's favorable. Releasing energy is easier to do. Now, when you have a positive charge and a negative charge, the sum of those, so if you think of +1, so if you have 1 minus 1, what do you get? Well, you'd get 0, right? So the idea is that you'll have a neutral particle. So keep these in mind, right? Positives and negatives are attracted because this is going to define a lot of our chemical bonding. And on top of that, the idea of having a neutral particle is very, very important. Now, how exactly can we try to figure out how the atom is looking? Well, this is something that required many generations of scientists to figure out the major portions. So the first part of nuclear atomic theory, so NAT, how exactly did it all start? Well, most of it started around Thomson, who originally who discovered that there were particles being emitted by gaseous atoms. So what he did is he made what is a cathode ray tube. And to think of what is a cathode ray, if you haven't had an old-fashioned television or maybe an old radio, think of maybe neon lights. So if you have like a neon sign that you see like outside of a bar or a store, right, that excited energy that's in there, you see the light that is being emitted. Now, what happened here is he drilled a hole in one side of this thing, and as a result, there's particles coming out and they were being deflected. So the thing is, though, the particles, as they were deflected, they were going between 2 charged plates. One was positive, one was negative. And if you remember from what I said before, opposites attract, you see that the stream of particles here are getting attracted towards the positive plate, and they're being repelled away from the negative plate before they hit the detector that they're going towards. So what the heck does that mean? All right, so that means that our particle, whatever this is negative. So what particle was negative before? Those were your electrons. So it has to do with something with the electron. This was the discovery of the electron. So at first, they believed that the atom was mainly this big negative thing. So if essentially there was all this negative atoms, and scientists believed and they knew that atoms were neutral, so how can one explain the existence of the negative charges that he was finding? Well, if there's a negative charge, there must also be a positive charge. So this is where the plum pudding model came from. Don't ask me about how the name came up, but essentially the way that he originally believed that the atom existed at the time was that electrons were embedded in a sphere of positive charge, okay? So being there's all these electrons that he could see that were getting repelled, they had to be embedded in this positive sphere. So, all right, you have this idea. Let's test it. So this is your hypothesis. How can you test this? Well, the way that he decided, all right, well, if I want to prove my idea that this plum pudding model is real, if there's this evenly spread out electrons across this big sphere of positivity, that means that this atom is mainly empty, that there should not really be that much inside of the material. That if I were to shine, let's say, a light through it, well, let's say if I put radiation through, let's say, a very thin gold foil or some kind of foil, then all the electrons should just go straight through. Well, what happened was when all the radiation got shot at this very, very tiny gold foil, rather than everything just passing through because it's going to be this low density environment, he saw the opposite. A lot of it passed through, as you can kind of see in this picture, but a lot of things were deflected. And in fact, some of the particles actually shot back, meaning they were deflected backwards. So how is that possible? How could it possibly deflect back if this big pudding model is all these little particles and they're very dispersed? There's nothing really in it. So what does that mean? What could they possibly be hitting like a brick wall and getting reflected back? So what this suggested is that inside of the atom, there is an area of very, very high density within the middle. The idea that there is a nucleus within inside of your atom. So this is where the beginning really all started. The atom has a nucleus, which inside of that nucleus contained almost 99.9% of the mass of the atom, and the rest of it is all mainly empty space all around the outside. So this is where many other experiments would come into play to really try to further define this, but to save us for the time, and we only really want to know about the basics. There were many experiments to figure out the rest, but let's just go through what exactly the anatomy looks like. This did take observations, it took measurement to really try to build an understanding. So the first thing is, there's a nucleus. So in the middle of the nucleus contains protons and neutrons. This contains almost all of the mass of the atom. It's about 99.9% of that mass. Now, outside of the mass is where the electron cloud is. So the electron cloud is generally it's where the electrons can be found. These things are very, very light. They are very dispersed, and they have the probability of finding them here within their orbits is somewhere in this general region. Now, what's the size that we're talking about an atom? Well, essentially, the size of a hydrogen atom is around 100 picometers. Now, if you think of pico as one of your prefixes, that's 10 to the negative 12 meters. So very, very, very tiny. So to kind of help you put that on the scale of how small we're talking about, that's probably about maybe trying to put probably the nucleus would be in the electron cloud. So if you think of the football field, that would probably be an electron cloud. If I put a penny in the middle of it, that's your nucleus. So the ratio of sizes that we're talking about is really, really tiny. And then, being that if we have one football field, that would be like probably finding that football field on the size of the Earth. It'd be very, 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 very small. So notice where all the subatomic particles are. In the nucleus, we have essentially all of the protons, all of the neutrons, and then the electron cloud is all the negative portions. Overall, everything is negative. Now, what about the rest? What else can we get from all this? Well, the size is very, very tiny. So the nucleus takes up a very, very tiny percentage of it. And this is mainly all empty space. So those are all like the main takeaways here when we're trying to summarize exactly what it is that we're seeing. That the atom, all the mass is mainly in the center, mainly all those neutrons and protons, electrons, all mainly empty space, and overall atoms are neutral. So from there, what can we really get from that? Well, when it comes to mass, well, in order to find the mass of any of the isotopes or atoms that we're going to be looking at, what we are going to do is define a new scale for ourselves, which is atomic mass units, or AMU for short. Being that the protons, electrons, and neutrons, their mass and size is extremely tiny. They're 10 to the negative 27 kilograms. I don't want to write that every single time. So what they did, scientists have done, is to find a new system. So every proton is equivalent to 1 AMU, and every neutron is also equivalent to 1 AMU if you just use one sig fig. So when we're adding up masses, we just add up the protons and neutrons. We do not worry about the electrons. So why can we not worry about them? Well, notice how the difference of size here. So that ratio is about a ratio of about 1800, and that's huge. That's a very, very large difference, meaning that you can ignore the amount of mass that is there. You don't have to worry about it when that's being calculated. Now the charges, that is very important. Remember, +1 for protons, -1 for electrons when you are figuring out your charges, and neutrons are always neutral. So this is the general idea of trying to look through all of these different species. Now, what the last important point is really focusing on what the importance of protons are. So one thing that you'll notice that the periodic table is organized by atomic number. And I'll say this in many videos, that's extremely important, because the atomic number, which is listed on top of any one of these elements, it's what tells you how many protons something like gold has, for example. Gold has 79 protons. Therefore, it has 79 protons in its nucleus. Now, so that means that any single atom that you ever will find of gold will have 79 protons no matter what, or it would not be gold. So every element has to have its number of protons in order to be identified as that element. So when we're talking about changing charges, which we'll be doing a lot in the future, we never change the proton count. We only ever change electrons. So keep that in mind, right? So the other thing to remember too is, all right, well, if I can figure out my number of protons from the atomic number, we can also figure out how many electrons we have. And that's because every single one of these species are neutral. So if I have 79 protons of gold, I would have 79 electrons as well. Now, we can also do this for other elements too. So if I have carbon, right, carbon has an atomic number of 6. So it has 6 protons. Therefore, it has 6 electrons because it's neutral. Same thing if I want to look at, let's say, something like sulfur. Sulfur, if you look it up on your periodic table, it has 16 protons. So how many electrons would it have? Is 16. And that's how we determine exactly what species that we have in all these. Now, all the elements that we have right there with all their properties and all their protons, right? We can see them all in the periodic table. They all are identified by their chemical symbols. So all their 1 and 2 letter abbreviations. Many of these are based on how you can spell them, right? When you're trying to identify exactly what it is that they are, but some of them are not so obvious. Some of them might be like off of Greek or Latin or all kinds of different names, but we're going to be learning all about them and trying identifying them by their protons, electrons, neutrons, and counting all those different species. All right, this is the end of this video. I hope that this helped you a little bit more understanding kind of some of the ideas of where all this came from. Biggest takeaway is knowing how that the atom has a nucleus, which has protons and neutrons. surrounded by electrons, which we will learn how to organize in other videos. Thank you so much for listening. I hope this video helped, and I will see you all later. Bye now.